Welcome to the fifth video of our introduction to EBSILON Professional. In this particular episode, I would like to discuss the difference between design and off-design calculations in EBSILON. Up to this point, we have designed our cycle for a particular operation mode. Usually we assume that the design case is the 100% load case. In order to simulate part load conditions, we will use off-design calculations. So let's take a look at the calculations in our design case. Whenever I simulate my cycle and the calculation is successful, the question whether I would like to take over the nominal values appears, what indicates that I am performing a design calculation now. So the first difference between design and off-design calculations is the fact that we are calculating nominal values in design modes. So I take over the nominal values, and the nominal values I have calculated right now can be found as blue values within all our components. In case of the turbine, I assumed that for a certain inlet temperature, a mass flow or volume flow, the turbine has an isentropic efficiency of 88%. And therefore I know what kind of outlet enthalpy I have in this certain load case. The same thing happened to the heat exchangers. If I look at the condenser, I have calculated the nominal value of the heat transfer or heat transition coefficient, Kan for nominal, which is based on the terminal temperature differences that I specified inside my component. In order to perform off-design calculations, I usually create new profiles in order to vary my load case and other parameters. Therefore, I open the Profile Manager and I create two new subprofiles. One subprofile will be my off-design 100% load case. The other one will be my 80% load case. Please note that the names of my profiles have to have a specific nomenclature, due to the fact that those profiles can be addressed by an EBSILON-specific programming language called EBScript, which will be the subject of a future tutorial. What we should keep in mind, there shouldn't be any blanks or mathematical operators and signs like a percentage sign in our profile name. So it should be basically called like you would call any variable inside a programming language. I open the 100% load off-design profile, and I see that it has exactly the same topology as my design profile. As no calculation has been performed yet, the value crosses are empty, and if we take a look at our components, we see that all values all specification values are gray. If I switch to design, they become black. So the gray color indicates that the values are inherited from a parent profile. Right now, my parent profile is the design profile, as you can see in this profile tree. So all values that are identical to the design profile appear gray within my property menu. As soon as I change those values, they become black. This indicates the advantage of the use of different subprofiles. I can create a design profile which incorporates my basic configuration and my topology and perform different calculations within my OffDesign profiles where I can change several parameters. So I can change parameters in different subprofiles without changing the whole topology and, for instance, perform parameter studies. I can also bring back the inherited value by pressing Ctrl D, and you see the gray number reappears. By this I can always restore the original configuration derived from my parent profile. So I can perform a calculation right now, which is successful. And you notice that the question whether I would like to take over the new nominal values doesn't appear, even though the values, the result values of this profile and the design profile are identical. You see the value crosses don't change. This indicates the basic difference between design and off-design profiles. Inside the design profile, I set the nominal values, or I calculate them, like in the case of a heat exchanger or a turbine. In the off-design case, I use the nominal values in order to calculate my off-design results. The results of my off-design calculations are based on my nominal values specified in my design profile, and here we have different options. First one, the off-design calculation is based on the characteristics inside my component, on physical equations, or on user-defined polynomials. I will try to give you an example on all of these three cases. So let's open the turbine and take a look at the design case. You see that there is a specification value called FCHR, which indicates the type of the characteristic I use during the off-design calculation. This characteristic is nothing else than a volume flow based function indicated by Vm1 and Vm1n for my isentropic efficiency eta I. This flag also allows me to change the relation of my characteristic. It can be a function of the mass flow, of the in and outlet pressure, and of course the default case, the volume flow. We can stick to the volume flow right now and take a look at the characteristic line. You see eta I divided by eta IN, the nominal value of my isentropic efficiency calculated in the design profile, is a function of FCHR, and it is specified within this table. Those are the characteristic points of my line. This means that at 100% volume flow, actual volume flow divided by volume flow nominal, so this means at 100% of my design case, my isentropic efficiency is exactly 100% of my nominal isentropic efficiency. At 95% of my nominal volume flow, the efficiency of my turbine will only be 99.98%. And so on, and so on. And all values in between those characteristic points can be interpolated by epsilon. In regard to the characteristics, we can also have a look at the characteristic lines of our condenser, which is now a mass flow based function of my heat transition coefficient Ka. But once again, what you should notice is that all values are always normalized by the nominal value. So you can always interpret those values in the table as percentage values. This also explains why the 100% load case actually should be the same as the design case, because at 100% of the mass flow, of the nominal mass flow, I have exactly the same heat transfer, or in case of the turbine, exactly the same isentropic efficiency as in my design case. So if all the heat transfer coefficients and the efficiencies and everything remain the same, then, of course, the result of my calculation should be exactly the same as in the design case. So let's simulate the 80% load case in order to make the concept of the characteristics more clear to you. I switch to the 80% profile, and in order to get the 80% load case, I change the reference value of my controller, which now will try to establish a power output of 120 megawatt. I simulate this. You see I get an output of 120 megawatt. And now we can compare. We can take a look at the efficiency of my turbine, which is now 87.99%. This value was originally 88% in my design case. So if I took the results of my design case and my 100% case, you see this value is almost exactly 88%. At 80%, my turbine efficiency decreases due to the shape of my characteristic line, which has a top efficiency at 100% of the volume flow and drops down as soon as I reduce my load case. What happened was that my volume flow changed from 100%, where we had a volume flow of 4.22 or a relative volume flow of 1, to a volume flow or relative volume flow of 1.152. And if I look at my char line again, I will see that we are somewhere in between those 2 points. And of course, if I interpolate between 1 and 0.995, there will be a value smaller than 1 that I have to multiply with my nominal value in order to get my actual efficiency, which is right now exactly 87.99% and not 88 anymore. In order to give you an impression how the OffDesign calculations perform based on a physical equation, I will introduce a control valve in between the steam generator and my turbine. All changes of the topology should be performed in the design case, because all the specification work I put in will be inherited to my subprofiles, which saves a lot of time. So I cut open the pipe and I add a control valve to it. This control valve allows me to have a higher pressure on the inlet and a lower pressure at the outlet. Now that I have added this control valve, the setting of my turbine, which indicates that the value is taken from outside, which in our case is the steam generator outlet pressure, should be changed to P1 calculated from P1 and set, which will be, just to give you an example, 95 bar. So 5 bar lower than the steam generator pressure. I can try to simulate this cycle, and I get an error input message. I have an error on my input data, and it indicates that start value is missing. The start value message is always a hint that something didn't work in regard to my controller. And as you remember, I specified that the start value of my controller is an external value, which was basically component 33 before. And of course, I can just transfer this component here in order to allow a successful calculation. Now let's take a look at the way my cycle operates in OffDesign. So when I switch to 100%, nothing should change in comparison to my design profile. Then I go down to 80%. And you see now that the values of my steam generator and the inlet pressure of my turbine have changed. So let's take a look at it here. So at 80% it's 77.68 bar. At 100% it was 95. The inlet pressure of my turbine is now calculated by the Stodeler equation or the cone law of Stodeler. We can open the help file. So the inlet pressure of my turbine is calculated based on the mass flow, the volume flow, and of course the outlet pressure of my turbine. Another example for an off-design calculation based on a physical equation would be the pressure drop in a throttle. So let's take a look at the throttle component, and we see that the part load pressure drop inside a valve, which nominal pressure drop would be 0.5 bar, is depending on the mass and volume flow or on the mass flow, or it could be even constant. We can again take a look at the equations, and here we see immediately the equation based on the actual mass flow, the actual volume flow, and of course the nominal values derived from the design case. The third possibility to influence the off-design calculation is the user-defined polynomial, or as it is called within EBSILON, the adaptational polynomial, ADAPT, which can, for instance, incorporate any kind of mathematical expression. So I could write the square root of 2 here, activate the use of my adaptational polynomial in combination with my chart line, or just solitary without using any kind of char line. Let's take it in combination with a char line. I will also change my polynomial to make it more simple to square root of 1, and we can change to the off design and simulate one more time. And basically nothing changes because the square root of 1 is of course 1. So if I would like to change the adaptational polynomial to 0.9, the value of my isentropic efficiency should change. And you see it really changed from almost 88% or 88% to 83.5. So you see this polynomial is really working. This brings us to the end of our video. And let's sum up one more time what we have learned in this particular tutorial. We learned about the difference between design and off-design calculations. In design calculations, we calculate the nominal values, which are then being used in our off-design calculations in combination with characteristic lines of my components, such as the characteristic of my turbine efficiency, which are also used together with physical equations, such as the pressure drop at the throttle or the Stodola equation, and of course the adaptational polynomials. All of those design and off-design simulations should be always split up in different profiles, in design and off-design profiles. And we remember each sub-profile has the same topology as the design profile, and it also inherits all the values from the parent profile, which then can be changed and also restored during the ongoing simulation process. In the next video, I would like to give you an overview of all the different applications that you can model within EBSILON.